share my screen. All right, so on the GitHub website, if you downloaded the whole repository, there are several documents in there. If you just want to follow along today, watch what I'm doing, but really don't want to be, let me see if I can hide these. Great, thanks. Okay, if you don't want to be doing it at the same time as me, you can follow this. I recommend you try to follow along in R with me. But if you ever come back through these materials or want to read through them on your own, it's this HTML file that's going to read like a file. It should kind of read start to finish, in order in English with code and output interspersed. All of the outline is here and everything's clickable too, so you don't have to scroll. But to follow along in R, I recommend opening the R Markdown or the .r file. The .rmd or the R Markdown file is the file that I use to create the HTML that you have access to. So all the same text that appears in the HTML file is here. It's just not formatted as nicely, right? So here's like where I'm inserting a lot of the pictures you're seeing and stuff. So it can be a little messy to go through, and it's not the most ideal way to read the actual text in the document. But to run any set of code in this, you'll find code in these gray boxes, which we call chunks. And you can always press this play button, or if you're inside a chunk, you can press the run button up here. You can run current chunk or run next chunk, and I'm on a Mac, so these are my hotkeys. If you're on a Windows machine, there's similar hotkeys if you want to learn those and use those. The .r file I created using this function right here. You can also open it, and if we were to do that, it has all of everything that's in the R Markdown that falls inside one of these gray chunks. That is in this .r file, but all of the text is gone. Okay, so this can be really easy just to grab the code. So however you want to follow along, you do what feels best to you. I always write my code so that the RStudio outline and code folding can be used. So if you see this button at the top of your RStudio where you have it open, in both the R and the RMD file, it's not as pretty as in the RMD file and actually doesn't work because it's doing kind of a weird thing. So I guess this only when you use that Perl function. This really only works with the RMD file, but you should be able to also navigate to sections according to their headers here. Okay, so again, if you're looking for something, you don't need to scroll all the way through. The last kind of PSA I'll give for all of these CSDE Intro to R workshops, I include the same two getting started sections because I never know if someone's coming for all three or just dropping in for one of them. So if you did come last week to June's objects and programming session, this R Markdown section and getting started section that talks about how you can install RStudio, how to set it up, and what R Markdown is and sort of how we use it. That was also at the beginning of the last file. So the meat of what we're going to go through today starts in the reading and the writing files section. The last thing I'll say is that before we get started, oh no. Here, if you're in the RMD file, I have this on source. This is where you write the markdown code and the R code, but if you put it on visual, you will see sort of a working version of the HTML file that still has the play signs or the play buttons for each chunk where you can run the code that way, but then everything else has been rendered and is nice and readable. So that is maybe the best way to go through this. So today we're going to talk about working with data. So in the last workshop week, you covered all different object types in R and some rudimentary aspects of programming that occur in any language and how they work in R, right? What their syntax looks like for a for loop, for a function, for an if-else statement or whatever. But we didn't focus so much time on how we manipulate objects that are data dot frames or tibbles, right? There's quite a bit given to you about how to subset vectors and matrices in that last lecture. And a lot of that is because I think that's getting taught less and less with tidyverse being so prominent, which is I think great. So there is the assumption that maybe some of you have a little bit of background on how to subset data frames or manipulate them already, but maybe you've not really worked with matrices and vectors in R. And then the other reason that we sort of defer doing things with data frames or tibbles until it's this workshop is that it's really a topic in and of itself. That's usually the bulk of the time that I think most of us spend on any project is actually in this kind of data cleaning and manipulation phase. Maybe not the most calendar time, but I would say it's usually the longest time I spend programming and double checking, et cetera. So we are going to focus today on first, how do we load data into R and save output files or output data? Then we're going to focus on how we get to know a new data set once we load it into R. And then we'll cover the main tasks of data manipulation, how you select a variable or select certain rows, how you modify an existing column or create new columns in a data frame. We'll talk about how you summarize data frames and then how you can move between wide and long formats of data. Any questions before we get started? No? Okay, so this is arguably the hardest part about working in R. And for those of you who use R projects or have been introduced to those, this doesn't come up quite as much. I tend to not teach R projects in the beginning of R because I think it's important to learn the details of this process of setting your working directories and your relative file paths. So if you want to read a file into R, usually a data file, and you want to write a data file or a figure or something else out, the most important thing you need to know is where that file is that you're going to be loading or where you want the file that you're going to be saving to land. And when you're reading a file into R, you have to tell R exactly where in your computer to look. So the place that R is going to look is what we refer to as the working directory. And this isn't just like colloquial. You'll see as I introduce you, if you haven't seen before, you'll see references to this phrase throughout the actual interface of RStudio. So you can tell right now, actually, first of all, let me zoom in. I know we're doing screen sharing, but this might be a little helpful. You can tell what your current working directory is by looking at the console panel of your RStudio. So it may just have a tilde, in which case that refers to your home directory. On a Mac, that's usually like your desktop, but it can be different things for different computers. You can automatically set that. I come of age, if you will, in an R generation where setting your working directory is the first part of any code that you write. As I mentioned with R projects, that has kind of moved away as an R project sets the directory that that project file lives in as the working directory, which is usually kind of what anyone intuitively wants, right? I created a new folder for a project. I put an R file in there. It would be really nice that when I open that file that R knew I was in that folder. So R projects in RStudio do that, but our regular R files don't. So if we want to set our working directory to a folder that we're going to use. There's many ways we can do that. I also want to say that if this is a tilde, or even if this is some directory and you don't know exactly where that is or what that means, you can come over to whatever corner of your RStudio pane has the Files tab, and you'll see this gear. If you press down on the menu, you can click the Go to Working Directory option, and it will tell you in more detail where you are, and it will show you what else is in that directory, and it will allow you to navigate up the scale. Note that regardless of what operating system you're on, what programming language you're using, there's some kind of overarching shorthand when we talk about file paths. Double dots always refer to the folder above the folder you're in, or the folder that contains the folder that you're in. A single dot always refers to the current folder that you're in. So you'll see that get used a lot, but you can see here, if I click on these double dots, I end up in this trash folder. Okay, so now if we want to set our working directory, which I'm going to need to, I'm in the, in a trash folder. That's bad. This is from the GitHub when I was updating this. There's several things you can do. One thing is you can navigate using this files pane to the folder that you want to set your working directory to. So for me, I'm going to go down to my workshops folder. I'm going to go to the intro to R2, and now that this looks like the folder I want to be in, then I can click on the gear again and say set as working directory. Okay. You notice when I do that, now my working directory has changed over here. And if you're following along on your computer, you should be setting your directory to the folder that contains the Seattle Pet Licenses file that you downloaded from GitHub. Okay. Another thing you can do is come to your session drop-down menu at the top, and there is a set working directory option. You can choose directory. It's going to open a file explorer window, and you can navigate within the way you normally do in your operating system to the folder that you want. When you get there, you press open. The final way, and this is actually the way that I usually do it because it's reproducible and then it makes it part of my code, is I can use code to set my working directory. You'll also notice that here, as I'm pointing this out, if you look down in my console, you'll see that there's actually two different set WD calls that have already gone into the console. Those happened when I selected set as working directory in this file pane, and when I just walked you through setting the working directory through the session, right? So doing the point and click method at the end of the day is actually still just submitting the line of code that you might write yourself. So if you want to know what your working directory is, you can use the get WD function and press enter, open and close your parentheses, and it will spit out your current working directory. If you want to set your working directory, you use set WD and you put your complete file path between quotes. And remember, the tilde here stands for home. So for me as a Mac user, my home directory is users / my Mac username. That is usually the C directory on a lot of Windows, but it could vary for you. Okay, does everyone have their working directory that wants to follow along set now to the folder where they have this pet licenses file? Feel free to just speak if you don't or need help doing that. All right. Okay, now that we've talked about the working directory, we are going to read and write our first file. So the way that you read a file into R, a data file in R, depends upon the file type. So what is the suffix of that file? And this is also true for when we want to save or write files. So if you have a CSV, there's an in-house function called read.csv. If you want to read more about that function or learn how it's used, you can always access the help document of any function, right, by putting the question mark symbol in front of the function name and pressing enter in your console. We can see here the read.csv. We can see the main arguments file, whether there's a header. We can see that that defaults to true so that we don't need to specify that there's a header if there is one. We see some other things that we could change, but hopefully we don't have to. And then all the other optional arguments, right? And you can read about what goes in there as you need. The main important one, though, is this first argument file. That's the main thing we need, and that's going to need to be specified as a character. So put the name of the file in quotes inside read.csv. And like I said, if you're in the visual editor, you can just press play here. You can also copy the single line of code and paste it into your console. And when you run that, you should see in your global environment now the pets data set. Has anyone been unable to load this data set? No? All right. So then I'm going to ask you to run these next two lines of code, and this is the write.csv function. Open and save is maybe how we think about it in a point and click scenario, right? When we're opening a Microsoft Word document and then we're saving it. In any computing language, we're always going to call this reading a file or writing a file. And so you're going to notice a pattern here that regardless of the type of data that we are opening or saving, that we're going to have read functions and write functions, or loading and saving. So here, write.csv is just the opposite of read.csv. We're going to save a data set now in a file on our computer, right? So you'll see here that we really are going to need at minimum two arguments. We need the file that, or the object name in R of the thing we want to save, and we need a file path of where we're going to save that. So I'm going to write the pets object into the file Seattle_pets_copy.csv. I don't want to name it this again, or I'm going to overwrite that file, right? And then this is really important. It's really not at the end of the day, but it drives me nuts. So I'm giving you a handy tip. If you do not specify row.names equals false in your write.csv call, what you will see when you write this to a CSV and open it in Excel or reload it into R is an extra column at the beginning called capital X. Maybe you've encountered this before. That just has the row numbers. The default row names for any data.frame in R are the row numbers. So sometimes a data object might be set up, or you might set up your own data object in such a way that the row names are actually meaningful to you, right? Maybe they're subject ID. In which case, maybe you would want to write .csv row.names equals true so that that comes with your data. I tend to leave my row names alone and have anything like that as another column in my data. So I am almost never in that scenario. And I don't really need an extra column that just says the row number that I'm on, right? So I always turn that off. So I do row.names equals false. So now if you run this code, and I'm going to go ahead and go to my working directory before I run this. So I'm kind of cheating because I've run this code before. So I'm going to delete this file first. All right. So you can see I have Seattle pet licenses.csv. And now when I run this, I should also have Seattle Pets copy, right? Modified most recently. Okay. So here I'm going to make a copy of this pets object in R, and maybe we should go ahead and look at this data. That's kind of the next step of this. But this data set that we're working with is kind of fun. It's an old download. There should be an updated file, but the city of Seattle actually makes publicly available this set of information about every registered pet in the city. So you get the kind of pet, breed information, and name information, which can be really fun. Okay, so I'm going to make a copy of this object. I'm just assigning this into an object called pets copy, and I'm doing this to illustrate a point in a second. But if you run this line of code, you will see over here now in my environment, I have two copies of the same object, right? They both have the same number of rows and columns, and they're called two different things. If I look, at the names of this object, you'll notice that there are all of these dots in them. And that can happen sometimes when you're loading CSVs or other types of files, and there are spaces or sometimes special objects, in this case it's spaces, in the underlying data's column names. And then R might automatically substitute dots or something in there to make them all one word, which is more in line with the requirements for naming objects in R, right? But here, I want to teach you how to write R data files, or .rda. And that set of the function that will allow you to write an R object is called save. And if we try to run that now, okay, I didn't get an error, but in certain versions of R and RStudio, I have been yelled at, which is why I wrote this code. So it's strange that that's updated now. It didn't want me to save this particular object type as something that had periods in the name of the columns for whatever reason. So here is just an example of some functions. We're using one called gsub. There's also one called grepl and grep, but this is just an introduction to some functions that allow you to look at character objects or find character objects or subset a vector of characters based on some quality of the string. So in this case, what I want to do is I'm trying to replace every period in one of these column names with no space. Okay, so this G sub stands like for substitution, right? So I'm searching for the period, but when you're looking for certain characters in these string or character set of functions in what we call regular expressions, the period already has a meaning. So if we are actually looking for the character and we don't want to use that dot as a symbol in a regular expression, we need to escape it. So sometimes you will see this, and if you were to look at the information for any of these G functions, you would find some talk about escaping characters, escaping patterns somewhere. Let's see. Anyways, if you read this whole document, it would talk about it. But that's why I'm doing this. There's a few characters like a caret, a plus sign, a hyphen, a dollar sign. Those are all special characters, so you would need to escape it. So these are the names of this pets copy object, right? And the way this function works, if we look at the argument it takes, the first argument is a pattern. The second argument is a replacement, and the third argument is X. That's the object that we're looking at. So here I'm taking the vector names pets copy, right, which we've already looked at, this vector of length 7. Oh, that's not right. This vector of length 7, and I'm going to search for this string. So every time I find a single dot in one of these strings, I'm going to replace it with whatever I put in the replacement argument, which is just a single opening quote and closing quote with nothing between it. Okay. So then I'm going to, if I were to just run this, you'll see what happens. Boom, all the dots are gone. Okay. So then what I'm doing here is just overriding the column names. Ooh. Right. So that's what comes out of that, the right-hand side, if I just run it in the console, and now I'm going to overwrite the column names. And just to check, right, we can look, the names of this object are indeed, now they don't have that, the periods, and we can save the object. Okay, now I'm going to remove this pets copy object from my environment. And the reason why is because there's a little peculiarity to how you load an R data function or R data object into R. We save with the save function, right? And we had the object name and the file. And now we load and with the load function. And one thing that you'll notice is that unlike read.csv, there's no assignment arrow for the load function, right? I'm not assigning the output to anything. I just run it. So when I run this line of code and you run it, you should have just seen that pets underscore copy was loaded back into my environment, right? So this is kind of a unique thing to the save and load functions and to the .rda file type, that when you save this object as an RDA object, when it's reloaded, it loads this object back into an object of the same name with that's formatted exactly how it was when you saved it. Okay. So just to show you what happens if you try, this is one of the most annoying bugs I run into all the time. If you try to assign the output of a load function to an object, you will just get an object that is a vector of length 1, whose element is the string of the object name or the character of the object name, which if you have code that works, that you're running, like, and then you add this in, can be a really hard bug to find. So that's just an FYI.
Jessica, quick
Yeah.
question. So when you saved it, when you saved Pet's copy, wasn't it already loaded into the environment? So I wasn't clear why we had to remove and load it again.
I removed it for the express purpose of showing you what happens
Oh, okay.
when we load it. And this is a very good point. These next few sections, like these read and write sections, I can't think of a reason why you would ever write code exactly like this ever. I'm just creating new object types to show you how to use the functions.
Okay, great. Thank you.
Okay. And then things will get a little more applicable to real life. But thank you for the question. So has anyone had trouble saving either the Seattle Pets copy.csv or Seattle Pets.rda? All right, let's talk about Excel files. Okay, so there are 2 packages that you have to install to read the new XLS. They're not really new anymore, but the XLSX files. You can uncomment this line of code by just backspacing and getting rid of that pound sign. So if you tried to run these 2 library lines and you're getting an error that the package isn't found, please comment this line of code and run that first. So the first thing we're going to do is write an XLSX file so that we have one we can read. And so again, just like the other write or save function we've seen so far, you have the object and then the name of the file that you want to save it in, except that in this function, that argument is called path and not file, right? And remember, you can always do the question mark in front of a function name to see the names of the arguments, etc., and how you use it. So, oops, I got rid of that. So I need to make this object again. And then I'm going to write. And once again, I'm going to remove it just for the purpose of illustrating what happens within your RStudio when you read an XLS file. So now in your files in your working directory, you should have seattlepets.xlsx. To read an XLSX, you use the read underscore XLSX function. I suppose it maybe goes without saying that the read function comes from the readxl package and the write function comes from the writexl package. And again, it's a read function, so we just need the file name. And when I run this, of course, the object has been loaded. Okay, many of you might be Stata users, but even if you aren't, Stata files or .dta files can be a really compact way of storing large data files, much like ASCII. So a lot of big data and publicly available or semi-publicly available data might come in DTA format. For example, the demographic and health surveys. You have the option of downloading an ASCII file or a DTA file. So it's pretty common that I'm working with Stata files, even though I rarely use Stata on my own. The Haven package is the package that I use to read Stata files. There have been several other packages over the years, but I think this is kind of the go-to one now. I will say that Stata tends to update, right? It's licensed software. So when there's a new version, there's often a little bit of a lag if there's a new type of data object that can be made in the new version between when that version comes out in Stata and when there's an R package that gets the ability to load that type of data. But there's always usually some sort of backward compatibility where in R you can still be reading and writing old Stata packages, and then in the new Stata you can still be loading old Stata data objects. So again, if you don't have this package, you can uncomment and install it. I'm going to load the library package. To save something as a Stata data set, I'm going to use write underscore DTA. The syntax otherwise looks exactly the same as the read or write XLSX. Again, I'm going to remove this object just so we can see what it looks like to load it. And then if I want to load a .dta file, I'm going to use the analogous read function. And again, I have pets copy here. There's a million other files. I didn't go over them all. I've loaded, as I say here, these other types of files in addition to shape files, which I'm not talking about. But my guess is that if it is a relatively used, commonly used, even mildly within a discipline type of file, someone has probably written an R package for loading it. So just Google. The other note I want to make is that in general, I think it is best practice when you're writing R code to load all of your libraries at the very top of your code, particularly if you're sharing it with other people, so that they know what they need to do to install all of their packages and get their workspace ready. In my workshop materials, I don't do this because I want you to know the package associated with the function that we're talking about. So I load it as needed, but this is sort of a do as I say, not as I do PSA. So that's reading and writing data. Any questions before we move on to exploring and manipulating data? No? All right. Okay. So data frames and tibbles. You should have talked about this a little bit last week, but there are basically two objects that contain what we would call, all of us would call data. That's a data.frame, which is a base R object class, and a tibble, which is an object class that was introduced by the tidyverse. Both of these are special classes of lists. So if you were there last week, you probably remembered learning that a matrix is a two-dimensional array in R, but it requires that every element be of the same object class. So you can have a matrix of integers, you can have a matrix of numerics, you can even have a matrix of characters, but you can't have one column that's a numeric and one column that's a character, and you can't have factors. So most of the time, all of our data, right, is a mixture of quantitative and qualitative information or categorical information about a subject if we're in social science, or maybe something else. So we want one object where we can mix object classes, and in any language, the object that does that is usually a list. And so a data.frame and a tibble are special classes of lists that have been created in R, where each object is a vector, each element of the list is a vector, and each vector has to have its own object type, but they don't have to be the same as each other. And then people wrote a bunch of code so that instead of viewing that as a list object of vectors, we get to view it as a spreadsheet, basically a two-dimensional array. So like every other object in R, there's a set of is and as functions that allow you to logically test what type of object you're dealing with. So if we're looking at our pets data that we've been working with, we loaded that first from a read.csv function. That is a data.frame. If I test it, right, it tells me that it's true. If I ask that the pet's copy is one, it's also going to tell me true. But if I load tidyr and dplyr, then I ask if it's a tibble. Oh, they don't have an is tibble function, do they? I always run into this. The main point I want to make here is that if we were to load something with a tidyverse package like read Excel or Haven, that object is going to be automatically loaded as a tibble and a data.frame. We can always coerce anything into a tibble using the as.tibble function. So if I currently do class on the pets object, I see it's only a data frame. If I do it on pets copy, it is a tibble data frame, and a data.frame. And if I want to coerce this original pets object to be a tibble, I can do it this way. It doesn't look any different here in our global environment. It's still under the data tab. And if I test if it's a data frame, it's still going to say true because technically a tibble is a special kind of data frame. But now if I actually ask R to tell me what its class is, right, I'm getting all three of these classes, okay? So that's kind of some annoying programming stuff, but just an important distinction if you're like, what is a tibble? It's just the tidyverse version of a data.frame. So every time I load a new data set in, I kind of have a set of functions that I run through to get to know my data. I have a million documents in my files. Like if I were to type the phrase first look into my file explorer, you're going to find a document for every project I've worked on and every data set that comes in those projects. So this is kind of how I get to know data. Take it or leave it. Some of this is definitely preference and style, but hopefully some handy tips. So the first thing you want to do is look at the first 6 rows or the head of the file. If you run this in the gray chunk, it's going to come out in this kind of interactive form where you only get to see a few of the columns. If you copy and paste this into the console or type it into the console, it'll spit out down here. So here we see we have 7 columns: the license issue date, the license number, the animal's name, species, primary breed, secondary breed. It looks like if available, and then the zip code of the registration. And I want to point out that if we use the head function on a tibble, what comes out looks a little different. So here it's really nice that when you do this for a tibble, you actually get the object class of each vector printed on top, whereas you don't get that for a head for a data.frame. But one thing I don't like about the tibbles is that if you use head with it and not all of the columns can fit in the current console window you have, it's just going to cut off the rest of the columns. So that can be kind of annoying. Now, if I want to get to know the variable names, which right now we have 7 columns, so looking at the first 6 rows kind of kills both of these birds, but often we have a lot more columns, right? So I might want to just look at the names and search through and see if anything looks interesting or recognizable to me. The names function and the call names function should do that for you. We talked about row names a bit ago. These are usually not informative in our objects or in the way most of us package our data, but when you're getting data from somewhere else or you've never used it before, it can always be useful to just check and see that there isn't hidden data, if you will, in the row names. Often another thing we want to know immediately is the dimensions or the number of rows and columns. Of course, in our studio, we see that up here. But I'm sure we've all had the experience of writing code, and eventually there's a lot of objects in your environment, and you don't always just, it's not easy to scroll through and see where everything is. So the dim function will give you the number of rows and columns, the 2 dimensions of the object. In row and in col, of course, give you the number of rows and columns. Length is unadvisable to use with matrices or data frames because it's actually going to return to you the number of columns. It's like the length of that secret list that's under the hood of the data.frame, which is 7 elements here. But I feel like length, when we're thinking about a spreadsheet, right, we're thinking about how many rows it is. So I would just avoid length so that you don't have any confusion when you're working with 2-dimensional objects. The summary function can be really handy. It for numeric variables, it gives you the minimum, the 25th percentile, the mean, the median, the 75th percentile, the maximum, and the number of missing values. So that's really handy to know right off. How much missingness do I have? Really handy to see the min and max, right? You have an age variable and you see someone is 999 years old, or you have a Likert scale and you see, some big response. You're already first, second into the data, oh, there's like a missingness code here, or that's a data error, right? And I'm going to need to dig into that. For a factor, it will show the number of observations by category up to some number of categories that can be printed in a few lines. But as you can see, for character, it doesn't really tell us much of anything at all. The str function can tell us a bit more. It's sort of like the head column, but in a little bit different format. It gives you the name of every column in your data.frame or your tibble, the object class of that column, and then as many of the first 4 rows as you can, or as it can print out in the area of your console. So that can also be really handy to just kind of get to know, okay, what, I saw I had a species column. What does that look like? Are we working with capital letters? Is that a numeric? And I need to go to a code book to find out that there's actually a categorical representation associated with that number, etc. As this data set we're working with right now called pets is just a bunch of characters, it's not very helpful for the next few things that we're going to run through. So we're going to load one of my favorite packages or install it if you don't have it installed, called Palmer Penguins. So you can just backspace and install, and then load the data or load the library. And then you'll use this data penguins line to kind of load the data. And now I'm going to use the summary function to get to know this new penguins data set that none of us have used for the first time. So you'll see that when I run summary here, I get the kind of information I was telling you about that's so useful from the summary function. Right off the bat, I know what all of our column names are, right? We have a species column, an island column, bill length underscore millimeters. Like, I don't even need to see the documentation for this data set. I know that that means bill length millimeters. I know this means bill depth. We have, what's the next one? Flipper length. Body mass in grams, sex, and year. So without even knowing or y'all knowing anything about this data set, already I'm realizing that each row is a penguin, right? I know quite a bit about this data. I don't really need to know much else. Of course, it would be great to read some sort of summary of their study. Are these tagged penguins? Are they observing them from far away? How are they measuring them? But we learn a lot here from this summary. So we know not only that each row is a penguin, but we know that we have 3 types of penguins and that we have no missingness for the type of penguin or the island on which we observed them. We know that we have 2 penguins for which we're missing all of their, every time I teach with this data set, I want to say the word anthropometric measures, but they're not humans. So I don't know what the penguinometrics are, but we see 2 are missing them. We see 11 are missing their reported sex, excuse me. And of course, we can't tell from this whether these 2 are part of the 11 or, you know, there's 13 total penguins with some missing information. And then we see the year in which we observed that penguin. Okay. Now, if I look at, and of course, we see the 5 number summaries here. Unlike human age, I don't know anything about penguins, so I don't know whether the min or the max are indicative of a data error, but I can tell right away that the min and the max don't look that different from one another, right? We're not looking at orders of magnitude difference. If I run the str function, I see, right, the name of every column, its object type, and then the first few objects here. And with a factor, right, I see the levels and then I see the numeric representation of that variable. One thing that we couldn't quite tell here, but I can see now, is that the flipper length in millimeters is measured in integers, right? But the bill depth is measured not in integers. It's a numeric, right? So that's like kind of interesting. We can see that we have the factor for males, and then that year is also an integer. Okay, so already these 2 functions, when I have data that isn't stored as a character, have been incredibly useful in telling me what's in this data and what I might be able to do with it, or what my potential problems might be with it, right? Where do I need to go look for missingness, etc. Okay, so sorry, this didn't work correctly, but if you want to use that, you can just copy and paste it into a browser. Here's just some background and some cheat sheets and stuff on how to use tidyr and dplyr to do down here to do data wrangling or data manipulation. And then there's also a comparison between base R and tidyverse. Whenever I teach, and next week when we do data visualization, I will also do it this way. I always teach base R alongside tidyverse. I think there's different tools for different tasks, and there are times when base R is better. There's times when tidyverse is better. People, I think, have intuition about one or the other, but as I mentioned before, I think having some knowledge of base R actually can provide you some pretty good programming intuition that's transferable to other languages in the future. So from last week, you might remember that if we have a data frame, I don't know how far you got into this, but in base R, we can use this $sign operator to get a single column of a data set we want to use. So we have this pets data frame. If I want to get the species column, I just need to write the name of the data frame and then the name of the column. If I put that in the console, you can see 1,000 times the word cat. And then of course there's 50,000 other entries that I'm missing. You can also use what you would have learned about last week regarding matrices, the kind of square bracket notation to specify the rows that you're interested in before the comma and the columns you're interested in after the comma. So if I want the first 10 rows of the species column, I can put this in my console, right? And I get the first 10 rows of the species column. If I want the first 10 rows of a subset of columns, I can create my own vector using the C function, the concatenate function, and put a bunch of names in characters, column names separated by commas, and then I can take any of those columns that I want. Okay. In tidyverse, there's a function called select that does column selection. So to use the select function, I need to first say the object that I want to, the data frame or tibble that I want to select a column from or a subset of columns from. And then after that, this would be the columns that I want to select. Right. And so again, here we see 1,000 rows of the word cat printed and then the 50,000 to go. So that's what I would call selecting variables. Subsetting data is how I would refer to selecting rows of interest, right? We want to find all subjects who are female, or we want all of the pets that are cats in this data set. So, to subset data in base R, we basically are left with Boolean logic. We also use that in the tidyverse, but we just use it in a different way. So if we want to create this new data set and we want to break this out by species, maybe the first thing I want to look at is what are all the species in the data set, right? And remember, unlike the Palmer penguins data set, the summary function didn't tell me this because this isn't stored currently in my object as a factor. Everything's just a character. So I don't even know what I've got going on in here. So if you're familiar with Stata and the tab function, the table function is the base R equivalent. It has this argument about what to do with missingness. I always turn it on this way and it will add a count of missing rows as well, only if there is missing rows. So if I run this, I find out that we've got cats, dogs, goats, and pigs. Okay, that's great. For whatever reason, I need just the cats, right? I'm doing something with cats. So I want to substitute down or subset down to just those rows. So let's break down how we do this in base R. So we're going to end up with an object called cat underscore base because we created it with base R. And then we're going to do it with tidyverse. And so I want you to be able to see that the results are the same, but we have different objects. So we're not writing over each other. So let's break down the right-hand side of this code kind of inside out. We first have this piece of code, right? This is the innermost part so far. And that's has a left-hand side and a right-hand side. So on the left-hand side, if I just copy this pets $species, we actually already looked at this, right? That's just how I grab the vector itself, the single species column of my data set. So we know that this code is taking that column by itself. And then double equals here is Boolean logic symbols, and it's testing it if every element of that vector, pets $species, is equal to the string on the right-hand side. Okay. So if I run this set of code together, what's going to come out is a vector of length 51,000 and whatever. But instead of being the string of species, it's going to be a logical vector of true falses, right? With a true everywhere that the species is cat and a false otherwise. So if I take then that category or that logical vector of trues and falses and put it before the comma inside square brackets for a data frame, I'm saying I want the rows where that logical vector is true, i.e., I want to retain only the rows where species equals cat. By not putting anything after the comma, I'm saying I want every column that exists. So if I run this, I'm going to get a data set of 16,829 rows, 7 columns. Oops. And if you recall from our table function, that is indeed the number of rows we expected, right? That's the number of cats in our data set. Any questions?
What was the species again?
So this is the we've looked at 2 data sets and we're back with the pets data set. So this is pet registrations in Seattle. And so the species is the species of the pet, whether it's a cat, dog, goat, or pig.
Okay. I was just trying to think of it in terms of columns and rows. So that's going to be
Yeah, so
columns, right?
it's a column. If we look at this, right? This is, for instance, this is a pet
Oh,
whose
okay.
was registered on this date, whose name is Tinkerdell, which I wonder if that is supposed to be Tinker Bell. Cat, domestic, we know it's a domestic short hair and that it was in this code.
Oh, okay. Yeah. Okay, that helps. Thanks.
Yeah. So I'm just subsetting down to all the cats here. Okay. So we kind of walked through this already. This is going to give us that logical vector. So if I wanted to do the same thing in the tidyverse, I would use the filter function, right? In base R, I have to do subsetting with logic. I'm still going to use this same Boolean logic statement, species double equals cat, but I'm putting it inside of a function now is all that matters. And you'll see making cat tidy. I get the same output, right? I get the same number of rows, the same number of columns. It looks exactly the same. So, do what feels good to you and what seems natural to you, right? You always have these materials to come back to. If you one day need to read code for an old paper and it's all written in base R, if you just want to do tidyverse, that's fine. But I don't think one is better than the other. I will tell you when I think that one is better than the other. So the other thing we need to introduce regarding the tidyverse is the pipe. One thing that people really like about the tidyverse is the way you structure passing an object to multiple functions in a row. So if I want to say, select certain rows, so filter my data, and then select only a few columns, to do that in base R, you could, I guess, technically do it in one line of code, something like this, right? Where I have a specification here and a specification for the number, or the column names that I want. But in the tidyverse, as I said, to get columns, we would use the select function, and to get rows of interest, we would use the filter function. So in the tidyverse paradigm, if I want to select rows and select a subset of columns, that's 2 functions that I have to apply to the data set, right? And in a base R framework, we would pass pets to one of the function and save the output, and then pass that output to the second function and then save a third object. So what's nice about the tidyverse is that it introduced to R this concept of the pipe, which is used in other languages, and particularly in SQL, that allows you to instead of doing that, or instead of writing a bunch of functions nested within each other that can be hard to read, you can write the functions in the order that you want the object to go through them in a nice and clean way. And so the pipe here is this % right arrow %. If you're on a Mac, you can do Command-Shift-M. If you're on a Windows, you can do Control-Shift-M. This will really save your carpal tunnels, particularly your pinkies, from pressing Shift all the time. So that will just insert the whole thing, so that can be helpful. So the way we use the pipe is that you start whatever object. Remember, we have some object that we're going to want to do multiple operations on, or multiple functions we want to apply to it. we start the pipe with just that object name, not a function. So I'm going to start my pipe with my pet's object, and then I'm going to pass it to the function that I want to use. Notice that when we use this filter function on its own, the first argument I needed to pass to it was the object I wanted to subset, followed by, filter by, followed by the logic that's going to allow me to filter. When I use the pipe, I only have to specify that second argument. This argument becomes implicit because I've started the pipe with it, okay? So if I run this, I'm going to get a carbon copy of what I got here in this line, but I just did it with the pipe, okay? So that may not seem very useful or novel, but as I mentioned, it is useful when we want to do multiple operations in a row. So if I want to filter down to the cats and then only select the primary breed column, right? Instead of saying, you could imagine that I might have to do something like select, filter, pets, species equals cat. And that is really hard for certain people to read or understand. Or maybe even worse, I start doing really bad coding practices and do stuff like this, right? We've all been there. That's pets 2. And now I'm going to save an object called pets 3 because I'm really going to remember when my R&R comes back in a few months what pets 2, 3, 4, 5, 6, and 7 meant, right? And then we would do, this would then be select pets 2, and then we would select the primary breed, right? So I could do it this way. That's terrible, hence the pipe. So if I want to just get one column, which is the primary breed of all of the cats, right? I can do it. Scrolling too fast. I pipe first into filter and then into select. For this specific set of operations, it doesn't matter what order. Actually, it does matter what order, I realize. If I put the select first, right, I get a data frame with just one column, and there is no longer a species vector to filter on. So it is important when you're constructing pipes to think about your order of operations. But we can always save the output of a multi-step pipe into something else. So here I'm going to run this code from above, but now I'm going to save it in a new object called cat breeds, right? Now you can see I have this 16,000 data frame with just one column, okay? Any questions? All right. Sometimes we want to modify an existing variable in our data set. I would say that the most common time we want to do this is like we have a string variable for state and people wrote Washington 30 different ways, right? It might be that we want to clean the data. I go back and forth depending upon the context of whether you should do that in the same column with all the mess. I tend to think if you're going to make a lot of modifications, that you should just create a new object altogether that's like the clean object, or you should create a new column that's the clean column. But there are a couple times where we might actually just want to overwrite a single column, right? Like maybe we want to convert grams to kilograms and we're never going to go back, doesn't matter. Or maybe we have a bunch of characters and we want to turn them into factors for the duration of our analysis. So if I want to, for our pets data set, start to deal with this character issue and turn these into factors, we'll just start with the species character vector. I'm going to create a copy of this pets object so we can modify it. And I'm going to use the factor function to turn this column into a factor column. So factor is a coercive function. It usually takes a character vector. If what you pass is numeric, it's going to turn it into a character vector first. And then it's going to take all the unique levels in the order that they appear. If you just pass a vector and create a factor out of it and assign a numeric level to that string. If you want the levels to be ordered in whatever way you want, maybe because it is ordinal, or maybe because you want it to be alphabetical or whatever it is, you need to pass the levels of that variable yourself, and then they will be ordered in the way you present them. So this code is going to take the pets base objects species column, right? I'm taking this column right here, and that's a character currently, and I'm going to turn it into a factor that has these 4 levels. So that's the right-hand side. If we first just look at pet species, we're going to get a bunch of characters, right? If we just run the right-hand side, things look mostly the same, except the quotes are gone. And now we see the levels printed out at the bottom of our new variable. So what I'm doing here with the arrow and the left-hand side is I am overwriting this. You can see why I might be against overwriting in most cases, because what if you mess up? Then you got to reload the whole data frame and run everything up until that point. But if something like this, as long as you test the right-hand side of your code before you actually overwrite, I think this is fine. So now if I run summary on this new object, I still get this annoying character stuff for all the other variables, but now for species, I can see the counts by factor level or categorical level, okay? To do this in the tidyverse, we use the mutate function. And so I'm gonna start a pipe. I start with the pets data frame. I want to mutate, so I pipe that data frame into the mutate function. And then the way the mutate function works is on the left-hand side, you're naming the column that is going to be the output of whatever is on the right-hand side. So the right-hand side, I have a pretty analogous factor function, right? And I'm referring to the species column. Since I'm in the tidyverse, I get this luxury of just referring to the column name and not needing that $sign. So on the right-hand side, I'm referring to the existing species column in the pets data set. What's going to come out is a pets tidy object where that old species column is overwritten and the new species column is the factor version. I'm going to do the same thing here with the primary.breed variable as well. And note there's an as.factor function that does like sort of force coercion into a factor, and you can't specify levels there. So there's just two ways of doing that. And so for primary breed, there's so many levels I can't even begin to want to write them out by hand. So we do this. And now we look at the summary. We can see, again, species, we get the counts. For primary breed, we get the top 6 primary breeds. And then it's not as though there's one other category called other. This means that there's an untold number of other levels to this factor, and there's 32,000 observations in total. Okay. Any questions? All right. Okay, so that was overwriting a variable, which, as I said, is something that we don't really want to do often. I mainly only do it for the factor case. If we want to create a new column, which is also something we often want to do, we're going to use the same principles in both base R and the tidyverse, but we need to give it a new column name. So I'm going to turn back to the penguin data set now and create a copy of it that I can manipulate. So this is the penguin's base data set. And here on the right-hand side, I'm going to take the body mass column that's in grams, right? And I'm going to divide it by 100 or by 1,000. So now instead of numbers in the thousands, right, I have numbers on the order of magnitude between 0 and 10, it looks like. And instead of overwriting body mass underscore G, I wouldn't want to do that, right? Because the title says the units. That would be misleading for anyone else who might look at this code again. I'm going to need to store this in a different column. All right, so I'm going to store this in a column called body mass kg. And since we're working in base R again, I'm going to use the $sign to refer to that column, even though it doesn't exist yet. But once I run this line of code, it will be created. And now we will see that we have an extra column here at the end that is indeed this column divided by 1,000. Okay. For the tidyverse, we're going to use the mutate function again. But what is going to be different this time is instead of before, right, we overwrote, or the variable name on the left-hand side was also the column in the existing data that we were manipulating, right? Because we were overwriting those columns. Here we're creating a new column. So we use, oh, this should say body mass underscore G. Divide by 1,000 on the right-hand side, but we're going to assign it to the column called body mass kg. This is doing it with the pipe. This first code is doing it with just the function, right? And so if I look now at this, we see we have body mass in grams, and we also have body mass in kilograms, but I made it in the tidyverse. Okay. Any questions? All right. So the next thing we're talking about is summarizing data. So we have our data. We talked a lot about what we do with the raw data itself, but one of our main data wrangling tasks is usually making summaries of the data, right? Like making a table 1 or something. So in base R, it's kind of hard to do this, but it is possible. There's a ton of statistical functions that give us all of the summary statistics we might need, right? We might want the min, max, the mean. We can do standard deviation, the variance, the median. We can get quantiles or percentiles by passing the probabilities for which we want them. So that's how we could get each individual number, right? If I wanted to give you a 5-number summary of the flipper length of the whole data. And then if I want to create a data frame for a table, like one way I could do it, which kind of sucks, is just kind of strong arm it, right? I create a data frame from scratch. I give a name to this new column called flip length mean, and then I write the code to calculate the mean of the vector called the flipper length, right? And I do the same thing for the standard deviation. And then if I look at this table, oh, that looks great. But if I want to put it in a publication, I'm maybe going to need to round it, right? So that's all fine and great. But you could see how if you have a bunch of variables or a bunch of measures you want to make of those variables, that this isn't going to be very practical and is really prone to error, right? To copy and paste or to write by hand that much code for each variable. So there's an aggregate function in base R. Notice we're running low on time, so I hope we can get through this. This is one of the places where I say base R can be better. The tidyverse syntax is going to be way simpler, but if it's ever slow, you need to stop, press the big red stop sign before you lose a whole day of work and rewrite this code in aggregate. I've had a lot of trouble with the tidyverse when I have a lot of groups. So usually we're not trying to get the mean of a whole thing, right? Our table 1 is a mean by sex or summary statistics by groups, right? So the aggregate function can take care of that kind of overall summary and by groups. The syntax is that we do a formula with the outcome that, or the vector that we want to summarize, the column in our data on the left-hand side, and then the tilde, which is how we do a formula in R, and then the right-hand side will have our grouping variables. So if we don't want to do grouping, if we want to do for the whole data set, we'll just put a 1. We tell it what data we want, and then we have to write out this list of functions of all of the summaries we want to do as a function argument. So here, I want to report the mean and the standard deviation for everything I put on the left-hand side, okay? And I write this as a function of x, so that's why I have an x here in my mean. Now, if I print this out, whoops, I get the same result as before. Not as nice of a title, I would say, right? I get these function names pasted onto the vector. So still would require some formatting, right, to put it in a paper or something. To do this in the tidyverse, it's similarly tedious. I mean, but about the same. We would just use the summarize function if we want to summarize the whole data set. And then I'm basically doing the same thing here, right? I'm writing the left-hand side, the column name I want the result to be, And then on the right-hand side, a function of the existing column names that is the summary I want. So unlike mutate, which is going to add a new column, summarize is going to return something with either one row, or if we're doing it by groups, one row per group. Okay, so this penguin summary tidy, again, is that same output. Okay, so this is just handy if you have a bunch of numeric variables and you want to get the mean of all of them. There's some kind of complicated syntax you can do with the summarized variable. I don't have time to go over it now, but if that sounds like something you do, I would play around with this and maybe like Google some summarize across where and read some blogs. To do summary statistics by group, which is the main thing we're usually trying to do when we're making a table one, you still would use aggregate in the base R example. Now, if I want to do more than one variable that I'm getting summary stats of, I'm going to use cbind on the left-hand side of my formula to add all variables. And on the right-hand side, I'm going to add my grouping variables separated by plus. So I want to look at species and sex. And then the only thing is these functions have to be able to be applied to all variables here. So if I had categorical variables, I wouldn't pass them in this function, and I'd need to write some other function to get my summaries. So now if I look by this, you'll see that, or at the output of this, instead of one row with these summaries, right, I have now 6, the males and the females for each of the 3 species. I have the mean and the standard deviation now for both of my outcomes of interest, right? And then I could clean this up to put it in a table. If you want to count the number of individuals you have using aggregate, you have to do this kind of annoying thing, which is create a new column in your data that just has a value of 1 in every row. And then you can use aggregate on that vector, that column, by your groups, and then use the sum function. And it's just going to add up 1 for every row, and you'll get the totals you need. Okay, so that's kind of annoying. But like I said, there are some times where it's really made a difference, like hours of computation difference to move to aggregate for me when I had lots of groups. So in this penguins data set, we saw when we just did that summary with the aggregate that we had 6 rows, right? Male, female, and the 3 species. What these aggregate functions didn't do is give us summaries for these people who are missing their sex, or these penguins, not people. So this is one thing that you don't have to worry about in the tidyverse. If we have groups, instead of doing this just the summarize function that we looked at before, we're going to do a group by before. And then you just separate the column names by commas that you want to form your groups. I always ungroup at the end of any grouping thing that I'm doing in the tidyverse because it will remember your grouping, and that can create some problems downstream. So this is the most succinct and best code for getting a table 1 by group. But like I said, if you have a lot of groups and this starts to run long, I would revert back to the annoying code. But this is way more straightforward. I think it's very easy to read and see what you're doing, and very easy to know what you might want to do. And plus, to get the total, there's a built-in function called the in function, and you don't have to do any of that weird stuff we did, where we had to create a new column. So now if I look at the summary from the tidyverse, not only do I get the 6 rows I had before with the same results, but I do get summaries for these missing values too. Any questions? All right, I'm going to try to go through wide and long data in 5 minutes. We'll see what happens. So if you aren't familiar with the concepts of wide and long data, it's important to think of a repeated measures design. Say you have a study, you see someone at baseline, and you follow up with them twice. In long format, you have 100, say you have 100 patients and you have perfect follow-up. Never happens. Then a long format data would have 300 rows. Each patient would, or subject would have 3 rows, their observation at baseline, first follow-up, second follow-up. In wide format, your data set would have 100 rows, 1 for each subject, and 3 columns of data, 1 for their baseline, for their follow-up, and their second follow-up. So often we kind of want to, we'll get data in one format or the other, and then need to massage it into the other format for different purposes, either for use in a model function, we'd need it in long format. But sometimes if we want to make tables, it's easier to do it in wide format. So we're just going to talk about these two functions, pivot wider and pivot longer. I'm not going to introduce the base R version of this, which is the reshape function, because it's terrible. Pivot wider and pivot longer are the most intuitive solutions to this problem that have ever come to R. And I don't think it's really worthwhile for anyone to learn anything else. So I'm going to create here, using the tools we just learned, group by and summarize, a toy data set so you can really see what's happening with these functions. So here I'm going to group by island and year in our penguin data set, and I'm just going to count the number of penguins we observed on each island in each year. And if I look at this data set, I have 9 rows, right? I have 3 islands, 3 years of observation, and then I have the number of penguins I saw in each row. This would be long format. In this example, my island is my subject and my repeated measures are in each year, right? And then I have 3 counts. So if I want to pivot this wide to make a nice table that's maybe rows are island names and column names are years, then I'm going to use pivot wider. I'm in long format. So I'm going to pipe this into pivot wider. I highly encourage you, I still do this all the time. If you want to do this in your work and you're like, that sounds useful for me, but I don't really know conceptually what I'm moving wide to long, go to the help document for pivot wider or for pivot longer and run through every example they have and make sure you understand like what's happening, because each one they're doing a different example of what the function's useful for. But it's really intuitive what they show you kind of what the purpose is. So I would run through those on your own time. But the gist of it, if we're pivoting wider, we need to know what the subject ID is, right? In a wide format, I need 1 row per subject. So how do I identify that? Is it 1 column? In our case, it's just the island column. This might be a set of columns that uniquely identify a subject, right? And then when it says names from, right, I have this long format and I want to get to a format where the columns are named 2007, 2008, and 2009. So I want my new column names in the wide format to come from the year. And then it needs to know where the values that are supposed to fill those new columns come from. And those are going to come from my in column, right? So if I run this, we can see this up. This is what it looks like in long format. In wide format, it looks like this. And it was relatively easy for me to do that, right? So then to pivot longer, we're going to start with this wide object and I want to get it back to long. Now I know I have these column names and I need them to become a column of their own when things go wide. So the names, the main pivot longer argument is calls. That's the columns that you want to move long. So for me, it's everything that contains 200. I could also list them out by name, but now I need to tell it what I want the new column that's going to contain the current column names to be called and what column I want the values to be stored in. And that's it. And I have back my original object. Okay. Any questions? I know we're right at time, but I do have a few minutes if people have questions. You're muted.
Oh, I was just gonna say super helpful, the base R versus the tidyverse comparisons.
Oh,
So thank
great.
you.
Yeah, of course.
Yeah.
Anyone else? Okay, well, hopefully I'll see you next week and we'll talk data viz. Let me know if you have questions. You can reach out at any time. Bye all. Take care.